Let us talk the modal response analysis this class, which is 22nd lecture in module 1. In the previous lectures, we discussed about the numerical methods used for finding out eigenvalues and eigenvectors, which are nothing but the frequencies and mode shapes. We have also seen that how they can be easily obtained using numerical methods, and they are comparable by all the 4 methods, by which we demonstrated by a couple of examples. So, we also understood the 2 important essential characteristics of dynamic system, which is the frequency and mode shape. Frequency is important because you will be able to design the system where you can keep away the band of frequency of the excitation force from that of the natural frequency of the system, so the system does not resonate. Mode shapes are important because one would like to know what is the modal contribution in the overall response of the analysis. So, we will like to discuss how the modal response can be made simple if you have the normalized mode shapes. Instead of having a generalized mode shapes, I want to normalize them with respect to mass or stiffness, but let us quickly see what is the advantage. So, essentially what we do is, if you have got a normalized mode shape, we will convert the coupled equation of motion to decoupled single degree equation of motion systems. So, if you have got n degrees of freedom, you have got n equations of motion. You will see here I can simply write an equation like this, let us say m10 0 m2 of x1 double dot x2 double dot plus, let us take only the system without damping, let us say k1 minus k2 and k2 of x1 x2 is set to, let us say 0 or f of t. If you expand this equation of motion, you will see that m1 x1 double dot plus k1 plus k2 of x1 minus k2 of x2 will become 0. Similarly, the second equation will also have, let us say m2 x2 double dot minus k2 of x1 plus k2 of x2 is 0. So, if you have got n number of equations like this, you have got x1, x2, xn, you will see that these equations are coupled. On the other hand, the first equation have values of response on x1 and x2 both. Similarly, second equation will have x1 and x2, third will have x2 and x3 and so forth. You will not be able to decouple them. Okay. So, if you want to really find out the x of t or x vector of this whole system, you have got to handle mass and stiffness matrix as a whole. You cannot decouple them. But if the mode shapes are normalized, you will see that the equation of motion will get decoupled automatically. So, the solution becomes very easy. So, we will take up an example and see. I deliberately find omega and phi which are non-normalized. I will normalize in respect to mass matrix, get a normalized vector, then I will transform the coordinates of the entire equation of motion from x vector to y vector, and I solve in y, because y will become single degree freedom system equations. Then I get back to x. So, this is what we will demonstrate today. So, there is an example. I will take a 2 degree freedom system example, because 3 degree will be slightly taking more time. We will take about 2 degree freedom system, but the demonstration can be applied to n number of degrees of freedom of any order. So, the advantage is when you have got the mode shapes which are orthogonal which are normalized with respect to mass matrix, it claims certain advantages. So, we will read them first. In the next lecture we will talk about the damping estimates in different mode shapes like Cauchy damping and Rayleigh damping. Then we will move on to modal truncation errors. I mean, if you want to truncate the higher modes, what would be the error in the overall response? We will talk about that later, which is very important in seismic analysis and inertia force dominated systems like offshore structures. So, we will take an example now and see what happens if I have a mode shape which is normalized, and how the coupled equation of motion will get decoupled by transformation of coordinates from x to a y system. Let us see how it is done. So, we will take this example for demonstration. Let us say my mass matrix is like this. Let us say my stiffness matrix is like this. And I do not have a damping matrix. I want to estimate omega and phi. Now, one can ask me a question, sir, what happens to my f of t? Please understand, omega and phi are essential characteristics of a given system. They will be and they must be and they should be present in a system even if the system is not excited. So, it is a characteristic which is natural property of the system. So, omega and phi estimates should not vary and depend on f of t at all. Okay. So, it is a free vibration characteristic essentially, it should not depend on the forcing function at all. So, f of t does not bother here at all in my equation, and of course, I do not want to include damping here because we will talk about damping estimates slightly later in the successive lecture. So, now we all know that there are 4-5 methods we know how to estimate omega and phi. Let us take up the conventional eigensolver system and try to demonstrate this to find out omega and phi 1 and phi 2 for this problem. So, we know to find the natural frequency omega I must say determinant of k minus omega square m and set it to 0, that is a standard eigensolver solution. So, the determinant of 2k minus omega square m minus k 2k minus omega square m should be set to 0. When I expand this, 2k minus omega square m the whole square minus k square should be set to 0. So, 4k square plus omega 4m square minus 4k omega square m minus k square set to 0, omega 4m square minus 4k omega square m plus 3k square set to 0. Let omega square be x. So, I get m square x square minus 4k m of x plus 3k square 0, which is a quadratic in x. So, I can solve x1 x2, which are the roots of this quadratic, can be so this will be 4 km plus or minus 16 minus 12 is 4 root km by 2m square. This gives me x1 as and x2 as, that is omega square and omega 2 square, as the lowest one is considered to be omega 1, because we have to verify omega 1 from the mode shape, but let us try to correct it down, we know that. So, 4 minus 2 is 2, so 2 km by 2m square, so I get k by m. Okay. Similarly, 6 km by 2m square, so 3 k by m. Okay. It would be omega 1 square is k by m, and this is 3 k by m. I want to find the corresponding vector, which is the eigenvector of this. So, the second step is to find the corresponding eigenvectors. So, the rule is simple, k minus omega square m x set to 0, Ax is alpha x set to 0. So, for omega 1 square k by m, let us say k, that is this value. These are all individual matrices, remember, it is not a single value of k and single value of m. So, we are talking about multi-degree freedom system equation. So, 2k minus omega square, I must substitute k by m here. So, k by m of m minus k again 2k minus k by m of m of, let us say phi 1 and phi 2 is set to 0, that is the first mode shape. So, this amounts to 2k minus k is k minus k minus k of phi 1 phi 2 set to 0. So, this shows that if we expand this, k of phi 1 minus k of phi 2 is set to 0, it says phi 1 is phi 2. So, there are two unknowns, there are two equations, but still we cannot, because both the equations will give you the same meaning. So, let phi 1 be phi 1 and phi 2 will also be equal to phi 1. So, the mode shape of 1, that is the first mode shape, will be equal to 1 and 1. So, since the first mode shape is positive, I can say this is the fundamental frequency of the given system, because there is no 0 crossing. So, similarly substitute omega 2 square as 3k by m. So, to find phi 2, 2k minus 3k by m of m minus k, 2k minus 3k by m of m, a matrix multiplied by a vector of phi 1 phi 2, but of the second vector set to 0. So, this implies minus k minus k minus k minus k of phi 1 phi 2 should be set to 0. This implies minus k phi 1 minus k phi 2 is 0. This shows me that phi 1 is minus of phi 2. So, let phi 1 be minus 1 and phi 2 will be minus of phi 1, which is plus 1. So, the vector is going to be minus 1 and 1. So, I got two vectors now here, omega 1 square is k by m and the corresponding vector is 1 and 1. Omega 2 square is equal to 3k by m and the corresponding vector is minus 1 and 1. You can always check that phi 1 transpose phi 2, just check this, or let us say phi 2 transpose phi 1, it will not be equal to 0. The cross product should become 0, but they will not. So, they are not normalized, okay? They are not equal to 0. So, I want to normalize it with respect to mass or stiffness, both. Let us see what happens if we do it with mass. So, let me find out. So, let us normalize the vector with respect to mass. So, that is phi 1 to be normalized with respect to m 1 and phi 2 to be normalized with respect to m 2, and so on and so forth, because we have got to multiply them with the mass matrix. Why m 1 and m 2? The advantage, the greatest advantage in dynamics, you please understand, the off diagonal terms are actually 0. If you do with respect to k, you see you will get some other different value, I will show you later. Okay. So, it is always advantageous to normalize them with respect to mass. So, if you look at the evolution of dynamics in terms of forming the equation of motion problem itself, the coordinates are chosen at the point where the mass is lumped. In a given system, mass is definitely lumped and only mode shapes represent the relative position of the mass. So, mass becomes very important focus in the whole dynamic evolution itself actually. So, in a given system, if you are able to identify the mass matrix and lump them in a specific location where you want to measure the displacement, I think 30% of your dynamics problem formation is complete, because all the exercises are focusing only towards the inertia forces. Okay. I could always normalize this with respect to k also, I will show you. If you do it with respect to k, you will get back the eigenvalues actually, I will show you how it is done. Therefore, we do not want that, we want this. Okay. The advantage is off diagonal elements are 0, you get a greater advantage. This will decouple the motions now, equation of motion will decouple, we will see how. So, let us do that. So, let me find out the value of m1. This m1 is not equal to this value, please understand. Okay. The notation may be same. m1 is a value with respect to which I am normalizing phi 1. This phi 1 of course not equal to this phi 1. Okay. This is a vector now, the full vector which is nothing but 1 1. The moment I say phi 2, it is minus 1 and 1, I am talking about the full vector now. Okay. These are elements of the vector, though the notation may be same, but do not get confused. Okay. So, I must normalize the first eigenvector, that is what I am saying, eigenvector with respect to the m1 value and subsequently with respect to the m2 value. So, what is that m1 so called? Let us try to find out that. So, m1 should be equal to phi 1 transpose m phi 1, because I have to normalize it with respect to mass matrix. So, let us do that. So, phi 1 transpose will be 1 1. The original problem is m and 0, 0 and m, okay, m and 0, 0 and m, because this is the example problem which I have taken for demonstration, m and 0 and m, and then this vector is 1 and 1, set it is 0. So, you can see the compatibility 1 of 2, 2 of 2, 2 of 1, you will get a unique value which is 1 and 1, only one value you will get. that value I am addressing as M1. This M1 is not equal to the M1 in the given problem. Okay. This is a value with respect to which I will normalize phi 1. Why? Because phi 1 is not normalized. Had phi 1 would have been automatically normalized, I must get this product as 0, which I am not getting. Okay. So, I am normalizing it. One can ask me a question that if I normalize, what is the advantage? Please wait, I will show you the advantage later. But let us first normalize this. So, can you do this? What is the value of M1? Simple multiplication, just find out what is the value of M1. So, M1 is going to be equal to 2M. So, therefore, normalized phi 1 should be 1 by root 2M of 1 and 1, that is all, simple. I will write down the value here, 1 by root 2M of 1 and 1, okay, normalized. Similarly, can you find M2? I say similarly, M2 should be equal to phi 2 transpose M of phi 2. Phi 2 is minus 1 1, M is M0 0 M and phi 2 is minus 1 1, should become, let us say, M2. And can you find what is M2? How much? 2M. So, can I say normalized phi 2 is 1 by root 2 M of minus 1 and 1. That is the problem. Okay. So, we got this value. Now, I will call a new term called modal vector, which is called as capital phi. Capital phi is nothing but 1 by root 2 M of each vector separately. So, I can even call this as a modal matrix instead of vector. Now, I give a new name to this, P tilde matrix. Now, let us check. This is step number 3. What did you do in step number 1? Step number 1, we wrote equation of motion, we found out omega and phi. Step number 2, we found out the normalized vectors of phi 1 and phi 2 with respect to the mass matrix M1 and M2. Step number 3, we want to check P tilde transpose M P tilde. Let us see what happens to this matrix. 1 by root 2 M of 1 1 1 1 minus 1 1 of M0 0 M of 1 by root 2 M of 1 1 minus 1 1. Compatibility is perfect because 2 by 2, 2 by 2 and 2 by 2, you get an answer as a 2 by 2. Let us see what is the 2 by 2 I get. So, this will be 1 by root 2 M of M minus M M 1 by root 2 M of 1 minus 1 1 1, which will give me 1 by 2 M of which will become, is it not? This advantage you get, this advantage. So, I can plainly say that P tilde M P transpose will become identity. Let us do this for P tilde K P, let us see what happens. Which implies Okay. Very intelligently we can interpret this slightly in a different way. See what happens. I can say P tilde transpose Kp can be written as omega square of, where this is an eigenvalue, because eigenvalue for these problems are k by m and 3k by m. Okay. So, when you have got a normalized vector or a normalized modal matrix which is generalized or normalized with respect to mass matrix, you get two advantages. One, the multiplier of this order will become identity, the multiplier of this order will give you the eigenvalues directly. Okay. So, when I encounter such multiplications in my equation, I need not have to do the multiplication anymore. I can straight away use these values and my equation of motion will become get thoroughly simplified actually. Okay. Now, let us apply this concept and try to decouple the equation of motion by changing the coordinate system from x to that of y. Why we want to decouple? Because if you change the transformation of coordinates to x to y, you will see originally the equation of motion is coupled. On the other hand, the term x1 will have reference of x2 and the term x2 will have reference of x1. Now, I want to have decoupling of these two. Okay. So, they will become individual single degree freedom system equations. Already we know how to solve a single degree freedom system, be it in x1, be it in x2, we know how to solve them. Okay. That is the idea. So, having understood this part, let us rub this and take this to the step number 4, where we will demonstrate the advantage of this procedure for solving the problem. Ultimately, I want to know the x vector of this equation of motion, which is my response vector. Step number 4. So, let x vector, which is the original vector, be expressed as p tilde of y vector. On the other hand, x1 x2 can be now expressed as 1 by root 2 m of what is the p tilde vector? Is this the p tilde vector, right? Of y1 y2. So, now mx double dot plus kx is set to 0, that is the original equation of motion. I rewrite the equation of motion because I know x vector is p tilde times of y vector. Therefore, I can say m x double dot vector will be t tilde times of y double dot vector plus k of p tilde of y. Using the same relationship as above, I can write this. I pre-multiply this equation by p tilde transpose, see what happens, p tilde transpose m p tilde y2 vector plus p tilde transpose k p tilde y vector becomes 0. We already know this is identity and we already know that is eigenvalues. So, let us substitute that here. Okay. Now, let us read this equation. y1 double dot plus omega square y1 is 0. It is a single degree freedom system actually, there is no y2 term in this. Similarly, y2 double dot plus omega square y2 is 0. You can say for clarity omega 1 square and omega 2 square because they are two different values. But originally equation of motion had x1 and x2 terms in both the equations. Now, I do not have y2 term in equation 1, I do not have y1 term in equation 2, I have decoupled them. Okay, now this is a single degree freedom system. So, if I have multi degree freedom system like this, I will have n numbers of single degree freedom system problems. Remember friends, this is applicable only when your mass matrix is diagonal. When the mass matrix has got off diagonal terms, this is not possible. Okay, you will not be able to do it. You may wonder, I can do with respect to k. If you do that with respect to k, you get omegas back actually. You will not get identity matrix. We have shown that already. Okay. So, the only possibility of getting identity matrix is if you do it with respect to mass and that mass is diagonal, off diagonal terms are 0. Usually it is a practice, but in offshore structures off diagonal terms will not be 0. There are examples I will show you where they are not 0. In that case, equation of motion cannot be decoupled, that is called coupled dynamic analysis. Okay. So, now I already know these are two independent, I can write here, two independent equations of motion of a single degree freedom system in y1 and y2 respectively. So, I can solve them. I already know the solution for single degree freedom system in y1. I write it in general. Step number 5, we know yi of t is not general. I may be either the first or 2, that does not matter. Yi of t, single degree undamped system, free vibration, yi of 0 cos omega I t plus 1 by omega I y dot I of 0 sin omega I t, that is a general solution. But I am not interested in getting yi of t. In fact, I do not want y1 of t and y2 of t. I want x1 of t and x2 of t, because my equation of motion is in x actually. So, let us apply this equation back again here. If you want to know x1 of t, so x1 of t can be 1 by root 2 m of y1 of t minus y2 of t. Similarly, x2 of t can be 1 by root 2 m of y1 of t plus y2 of t. Okay. Now, the problem is very simple if you know y1 of t and y2 of t. Now, the problem is complicated because y1 of t and y2 of t depends on initial conditions on y of 0 and y dot of 0. I do not have them with me, I have only x0 and x dot of 0 with me. The original boundary conditions given in the problem are related to x only. So, I have to convert those original conditions on the y frame, substitute them here, get yi's, put them here, get xi's. Now, to obtain x1 of t and x2 of t, one should know y1 of t and y2 of t, but y1 of t and y2 of t depends on y1 0, y1 dot 0 and y2 0, y2 dot 0, which are not known. But however, x1 x2 was equal to p tilde of y1 y2. So, now I can say y1 y2 can be equal to p tilde inverse of x1 x2. So, p tilde matrix already we know. Let us find p tilde inverse. Can you give me this inverse? Yeah. 1, are you saying row wise or column wise? 1, that is all. Now I can expand this. Y1 of t will be equal to root 2m by 2 of x1 0 plus x2 0 of cos omega 1 t plus 1 by omega 1 of minus x1 dot 0 plus x2 dot 0 of sin omega 1 t. These values I already know because they are at zeros, initial conditions, they are not the answers. x1 of t is the answer, okay, which we want for the original equation of motion, but they are x1 of zeros and x1 dot of zeros, which are initial conditions of the given problem. We already know them. This is also going to be positive only because I am going to multiply the row with the column. This is also going to be positive only. Both are, because they are both are to be collected with x1 zeros and x1 dot zeros. Similarly, y2 of t root 2 root 2m by 2 of minus x1 x2 0 plus x2 0 of cos omega 2 t plus 1 by omega 2 of minus x1 dot 0 plus x2 dot 0 of sin omega 2 t. The moment I know y1 of t and y2 of t, I can get x1 of t and x2 of t from this equation because P tilde matrix is known to me. So, that is the advantage you have when you got a modal matrix. So, this is called a modal matrix P tilde, which is a normalized vector of the corresponding eigenvalue pair, which is normalized with respect to the mass matrix. Why? Because mass matrix got off diagonal term 0. When you multiply this vector or this matrix with the mass matrix, you will get an advantage of the identity which is being used in decoupling the equations of motion to solve them easily as equivalent n number of single degree freedom system models. So, it is very easy. So, we have never solved any matrix here at all, we simply used only the single degree freedom system knowledge and found out the solution for a 2 degree freedom system problem without actually solving any matrix at all. So, this will be easy if you have got a large size of matrix, because this is repetitive, you see this is repetitive. If you know the initial conditions, this is repetitive, you can plot. Okay. So, it is very easy to decouple them provided the two conditions. One, the mass matrix becomes off diagonal term 0 and the normalization is done with respect to the mass matrix and not with respect to k. If you do that, you get eigenvalues here actually. So, that is the advantage. So, eigenvalues and eigenvectors both are very important in dynamic analysis. When you are not able to normalize them, you call that analysis as coupled dynamic analysis. When you are able to decouple them, you can easily solve the equation of motion like this. Most of the cases in engineering, generally people use this technique to solve n number of equations of motion to get the solution. That is, the solve means what? You must get the x1 of t values, okay, x1 of t values. Let me, for completion sake, let me write this also. So, I will remove this here, I will write. For completion sake, let us write this. So, knowing y1 of t and y2 of t, x1 of t, x2 of t can be simply found out as p tilde of y1 of t and y2 of t, because p tilde is known to me. So, the multi-degree freedom system equations of motion are decoupled using the above procedure. It is solved. So, in the next lecture we will talk about estimating of damping in different modes. Probably we have found out an equation of C or estimating of zeta only for a specific single degree freedom system problem. If you got multi degree, then the modal the damping coefficient in each mode can be evaluated separately, that is important. Which mode is damped larger and how much. So, we must have estimate of damping in different modes, which we will discuss in the next lecture. So, there are two methods available in the literature, which we will discuss both of them. One is Rayleigh's method, other is Kahe's damping method. We will discuss both of them and see what is the advantage, what actually the model followed in offshore structures. Okay. And we all know that damping essentially comes from 2 zeta omega n. So, it is actually a dependent variable of k and m. So, the damping should give me a proportion of k and proportion of m, okay, that is the idea. What is the proportion? If k is 100% or m is 100%, in what mode and how much, that is the idea. How to catch this idea is what we will discuss in the next lecture. So, is there any doubt now at this stage? So, we have discussed about 22 lectures successfully in dynamics first module, where we are talking about the fundamental of dynamics, which is applicable to all types of structures, not only ocean structures. But application of these ocean structures in terms of design is very important, which I touched upon in my previous lectures, as well as in my textbook also given relevant examples how to relate this to the design concept in dynamics of offshore structures. But we will extend this study in detail to arrive m, k, c and of course x of t, that is the vector, for a given problem whose f of t is taken from earthquake load, wave load, current load, etc., a real life problem. We will take up a TLP, a real life offshore structures. We will also discuss offshore structures of a new generic form, which we have developed at IIT Madras, patented to IIT Madras. We have got excellent structural forms which we patented to IIT Madras, which has got very good representation in the international literature. So, we will discuss about that experimentally, analytically, numerically the results, which will be very novel idea for research frontier, research domain in terms of dynamics applied to ocean structures. There we will emphasize on ocean systems more in detail. Once we understand the second module thoroughly, the third module will be for advanced dynamics, where I talk about stochastic dynamics, which will be completely advanced in terms of dynamic application in any type of structure, especially in offshore structure, where fatigue loading becomes very important in terms of tether pull out, stability of structural challenge, etc. So, that will be very interesting. So, that is the area where we are going to touch in module 3, that is the whole program. So, friends, the examination for the particular course is now open in NPTEL. You have got to register for the examination, it is not free. For NPTEL it may be the course structure is free under MHRD, but for examination a bare minimum charges are being levied for conducting the exam all over the country, in fact all over the world as well. So, the examination registration is already open, it will close on 9th March. So, we have got about approximately 2200 participants listening to this course now internationally, from about 250 participants from countries other than India, remaining all are from India. So, you can compete your intelligence with about 2000 international or 2000 students, where many of them may be practicing engineers, many of them may be research scholars by themselves, many of them may be faculty. Okay, so, you will really know where do you stand in terms of your, because your certificate will indicate a percentile performance in the course. I do not know, it is a unique opportunity, you will never get this opportunity back again. You may get a grade in the class of maybe 30, 25, who all does not know dynamics at all, fine, getting S grade in that is not very good index of your intelligence, whereas getting a grade now in this case in percentile, competing internationally with people who know the dynamic subject is very important, and it is very interesting that where do you stand will rate you. So, that is important. So, the registration is now open for the exam. Please register online, then you will attend the mock examination, and the exam will be conducted at the end of 9th and 16th of May. It is available in the website of NPTEL. Please see that, and most importantly now start referring to textbooks where you will see the clarity, okay, what people actually talk about dynamics in terms of application. You will find maybe there are n number of textbooks available in the market. I am respecting all authors, all publishers who have contributed to this domain of research for the past about 30-40 years. With respect to all the authors and all the publishers and all readers, I want to make the statement open in the web domain that clarity in terms of understanding dynamics applied to structures is very rare, okay, it is very rare. I am handling the subject for the past 23 years, okay, it is very rare, clarity is missing actually. So, you must be intelligent enough to select this book which you want to follow. Now, if you open some of the textbooks which is listed in NPTEL, you will find that you will enjoy reading of dynamics like reading of any casual arts and science magazine. This is where dynamics is made easy in through lecture media as done in NPTEL, okay. This is the actually mission of NPTEL. We want to actually make the subjects which are very difficult for people to make it as easy as possible. We do not want to take you intrinsic vertical, we want to take you to make first the subject friendly, subject easy, ready references available, text is conveyed easily, numericals are solved in your presence with the calculator. You have a confidence, yes, I can now do dynamics as a friendly subject like a simple mathematics course. Once you get that confidence, research of writing equation of motion, solving them for a new structural form, which is an essential part of offshore structural research itself, because we all said offshore structure is moving towards deeper platforms, deeper water depth exploration. The conventional forms will not work. So, you have to go for a new structural forms. For all new structural forms, there are no ready made solutions available even from the start stage of design itself. You have got to start from yourself. So, you must know how to derive m, you must know how to derive k. If you have these two, how to adjust k and m in terms of omega not coming in the bandwidth of omega bar. So, the design and dynamics should be coupled as a research perspective in the domain of research of offshore structures. This subject of this module will certainly definitely help you to understand, make the subject user friendly first, make it comfortable and convenient even to a undergraduate student. That is what our aim is, okay. So, try to compete your intelligence level in terms of examination in this course, understand where do you stand. Why I am giving this preamble, because as you move towards a lecture module in module 2, you will find they are going to be slightly of an higher order of difficulty, okay. Many people amongst you or amongst the viewers may not focus on module 2 as comparable to module 1. When I move to module 3, about 70% of them will off from the subject actually, okay. Only people who have understood module 1 thoroughly will take themselves to be prepared to module 3, otherwise remaining all will float in module 1. Interestingly, institutes and departments which teach oceans engineering only will take you to module 2. All other departments or engineering programs where people do not apply them to ocean structures will have no speciality in dynamic analysis, because I will show you examples where my k is unsymmetric, my m is off diagonal terms present. This is a very unique problem only in ocean engineering. Therefore, attending to this course in ocean structures gives you an actually add an advantage which will throw light on second module. So, first let me make you to understand it is comfortable. Why I am saying this statement? Because if you are not able to understand the first module thoroughly, if you are halfway here, be sure that you revise the complete lectures of module 1 before you attempt to touch module 2, otherwise it will be very difficult, okay. So, try to rehearsal all the lectures and numerical examples and tutorials given to you, at least follow couple of textbooks, read lot of journal papers to develop interest in dynamics, okay. Thank you.